All right. In our last video, we took a look at the Kepler problem, which in essence is a planet orbiting around the sun, or a two-body central force problem. And by changing our perspective, by changing how we perceive the motion in front of us, we were able to drastically increase our analytical ability and capability. What do we find? We found that we could reduce a two-body, 6 degree of freedom problem down to a one-body problem with 1 degree of freedom. In essence, we found that perspective provides your once weighty eyes, and it gives you wings. By changing how you perceive something, how you perceive the motion in front of you, or in the language of physics, by changing our reference frame, we're able to drastically increase our analytical ability because it's much easier to handle one equation of motion with 1 degree of freedom. Drastically simplifies our lives. Now, what I want to do in this video is take a look at a quick example that allows us to take a step back before we chug ahead with trying to take the one equation of motion we have and trying to analytically solve it. And I want to take that time to examine the effective potential energy we determined, because remember, in that video, we determined that we could reduce this problem of a planet orbiting a sun down to one equation of motion with one relative coordinate r, which is basically the distance between the two masses, with a potential energy or an effective potential energy as follows. Basically, a component from the gravitation u sub r and a component which is related to the angular momentum, which is this term here. Now, what I want to do is to take that time, I want to examine a similar problem. It's still the Kepler problem, but instead of having a planet orbiting the sun, let's question what would happen if we had a comet coming in towards the sun. What's going to happen? Is it going to go around the sun and then orbit it perpetually? Or is it going to come into the sun, go around it, and slingshot out into outer space? At this point in the problem, at this point in analyzing the two-body central force problem, can we deduce anything else? Can we deduce any kind of additional behavior associated with that scenario based upon the mathematics we have now? Okay, so what I want to do to analyze that is take another look at U effective. What is this telling us? What is this communicating to us? Can we get any information out of it before solving the equation of motion? Okay, so to do that, what I want to do is I want to plot this guy up and divulge what it's telling us, divulge what it's communicating, because it's going to communicate very important ideas, not only to the problem, the Kepler problem that we've been analyzing, but also in subsequent areas in physics that you'll study in the future, such as quantum mechanics with the diatomic atom, things like that, okay? Or I meant to say diatomic molecule. So, if we try to plot this guy up, we see that there are two contributions. And before we proceed, I want to note that if we have a comet that's coming in, this u sub r, the potential energy, is just the potential energy we derived in one of the first videos associated with this series, which is as follows, which is negative times the gravitation constant g times mass of body 1 times mass of body 2 over the distance between them r. So when we examine the comet problem, the effective potential energy is no different than negative g times the mass of the comet times the mass of the sun over the distance between the comet and the sun. So similar setup, just instead of planet Earth, now we have a comet that's coming in, okay? So, with that in hand, we have to write down the angular momentum component. What does this tell us? It tells us that the graph is going to have two contributions. There's going to be a contribution from the gravitation, and there's also going to be a contribution to that guy, from that guy. So I'm going to call this U sub g for the gravitational contribution, and I'm going to call this UCF, basically the contribution from the centrifugal force. Okay, so what we know is that at different points on the graph, either this is going to dominate or this is going to dominate. So I've drawn down the final result, but it's important to note that the final result, which is in black, is a combination of UCF, this guy right here, and U sub r, that guy right there. It's not surprising to find that UCF is 1 over r squared, so as r increases, the function also decreases. So r increases, the function decreases. When r decreases, it blows up. That's why we get the shape as such. We get the similar shape as in here, just the derivative is a bit different because we have 1 over r, so that's going to affect what the derivative is going to be, but we have this negative term here, so it's basically this graph flipped. And we see that this is sort of a combination of the two. So let's explore what we can find out by, I guess, questioning the position of the comet at different points, okay? So I'm going to erase that. Keep that in mind, though. So what I want to question is, I guess, it's a limit. The limit as r goes to infinity. Basically, when r is very large, okay? So what do we find when r is very large? When r is very large, we find that both of these terms, the term including the 1 over r squared and the term including the 1 over r, are going to drop out, or rather approach 0. However, the real question is, relative to each other, which one is smaller? Is the 1 over r squared smaller, or is the 1 over r smaller? Okay, so the real question becomes, which term is smaller? The 1 over r squared versus the 1 over r. To test this out, we could take a test case. What if r equals 100? And that's a large number, but it's not close to infinity. So if we have 1 over 100 squared versus 1 over 100, obviously when you have a big term squared on the bottom, this term is going to be smaller than that term. And we can see that illustrated magnificently if we add them together, because this term is just 0.0001 versus 0.01. So when we add them together, that ends up becoming 0.0101, which is approximately equal to 0.01, depending upon what kind of accuracy we want to have. So as r approaches infinity, what's going to happen is this phenomenon is going to get pronounced to a point that we can essentially assume that this guy is that. So what does that mean? That means this term relative to that term is going to be much smaller. We can say 1 over r squared is going to be less than 1 over r. And in essence, this term here is going to drop out, and that's going to affect u effective. What we can assert in essence is that u effective is approximately equal to this term, right? Negative g mc ms over r. So that's why when we get to infinity, the graph starts to converge upon u sub g, okay? What else can we figure out from this? What else does this divulge, in essence? What we can do is we can start questioning, what's going on with the derivative. That's going to help us draw the plot. And it's also going to divulge a lot of the physics. So let's start taking the derivative, okay? U prime of f sub r is basically, we're going to take the derivative of this term first, because we're taking that guy. So 1 over r is going to give us negative 1 over r squared. So the negative is going to cancel out. We get g mc ms over r squared. So we get that term. And then we have to do the same thing here. So the derivative of 1 over r squared is negative 2 over r cubed. So the 2's are going to cancel out. And then we get that negative L squared over mu r cubed. Now, as r approaches infinity, what we're going to find is that this guy is approximately equal to this guy. Right? So it's going to be a positive g mc ms over r squared. So that means the plot is sloping up, which we see like as such. And if we step back a bit, I want to explain this a bit more. It's positive because we have r squared on the bottom as opposed to r cubed. So this has a higher magnitude. When r goes to infinity, this is infinitely larger than that guy. So we can neglect this. It's just like what we would do with Taylor series. If you've taken my course, that crops up quite a lot. In essence, we take the first term and the leading terms vanish when we have small r's, right? Because a small value squared is not as small as a small value to the fifth, for example. Okay? This drastically exemplifies that fact. So we got general behavior at r goes to infinity, but what can we say about the physics? What can we say about the physics? So if we take this and note here, this guy is no different than this. So we find that r prime prime, if this is positive, r prime prime is negative. So that means that far away from the sun, the comet, the distance between the comet and the sun, right? As we saw in the previous video, r is the distance between the two. It wants to accelerate towards the sun. So at this point, it wants to flow back down this potential well. It's a key word. You'll hear that coming up a lot in this video and in subsequent physics. It wants to go down this potential well, like a track. So it wants to go back towards the sun. So we got some general behavior at r goes to infinity. But what can we say for the limit as r goes to 0 when we get closer to here? How did we get this behavior here? And what kind of physics can we divulge about that? So when r goes to 0, what we find in the effective potential energy is that this guy is smaller than that guy. Why is that? Because if we have 1 over r and we're comparing it to 1 over r squared, basically these two terms, we find the following. Because let's take an example. Let's try 1 over, or when r is equal to a quarter, 1/4. So then we're dealt with 1 over a quarter is 1 over 1 over 4. 4 pops up versus this. So just something that isn't very small, we're multiplying by 16 as opposed to 4, much larger. As it gets smaller and smaller and smaller and smaller, this effect gets drastically amplified. What if we have 1 over 1,000? Then it's like that, right? It's like that. So this term is going to dominate over that. And what we find is that, this is the case, the effective potential energy is approximately equal to L squared over 2 mu r squared. So that's why it converges upon that plot. Okay? But we can go a step further. We can take this guy here, the derivative, the effective potential energy derivative, and figure out how it's changing. Okay? So in this case, when r approaches 0, this term here is going to dominate, right? It's going to dominate because we have 1 over r cubed compared to 1 over r squared. It's the same argument we had with this, but more pronounced. 1 over a small value cubed is going to be much larger than 1 over a small value squared. Okay? That's just how it's going to work. That's just exemplification of the math. Okay? So this guy is going to be approximately equal to negative L squared over mu r cubed. Okay? So it's going to be negative. It's going to be negative. That's why it's sloping down. It's sloping down. So we could take this fact along with our equation of motion and discover some physics regarding what the comet is going to do. So r dot is equal to the negative of this. So, and I meant to say r double dot. R double dot is positive in this sense. So we find that when the comet gets very, very close to the sun, at this point, that it wants to fly back out, okay? It wants to fly back out. So our double dot is positive, the acceleration is positive, and as the comet flies in, it's going to reach a point in which it wants to go back out, okay? So using this information, we're able to plot this guy, and we find that both the motion and the effective potential energy is a function of the gravitational potential energy and the centrifugal force potential energy. So what's important to note is that this is a potential well that's going to crop up very often in any kind of two-body force problem, and we're going to find this with the diatomic molecule. It's going to have the same behavior. It's going to have this oscillatory behavior in which, far away, it wants to come back down. When it's close, it wants to push it back out. So this is sort of like a track upon which the motion has to follow. And it's going to go whoosh, 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 whoosh. And furthermore, that jives well with our intuition. So this is sort of like a check. The mathematical framework we were able to derive by using our analytical pries, our ability by choosing how we perceive the problem and the motion, it jives well with what we would expect. We would expect some kind of oscillatory behavior. Because that's what we see in the night sky, right? So this is further proof of that. But my question for you is, can we go further? Can we still dive down further into the rabbit hole and discover more about this problem? What I'm going to assert is that before we actually go and try to solve this equation of motion, we can still learn more, okay? In essence, we verified the general behavior of the motion. That was conveyed with U effective. Now, let's figure out if we can say, are there certain cases associated with this motion? Maybe the comet is going to be bounded, where it's stuck in a perpetual loop. It's stuck in this potential well. Maybe it's going to come in, and it's going to be unbounded. It's going to slingshot around. Can we figure out anything else in regards to these questions, but just taking a look at the effective potential energy and our plots? What can we find out? To answer that question, we need to dig a bit further. In essence, what we've done, we've got a skeleton, a backbone, a nice framework for analyzing this problem. Now we need to fill in the meat on those bones, right? We need to fill in the missing details. And in order to answer that question, before actually solving our equation of motion directly through analytical means, what I'm going to say is there is one component we have not discussed yet that is buried beneath the details. What we need to do is pull that out from beneath the surface and figure out what it can divulge. What is one conservation law that you usually explore in Physics 101 that we have not considered yet? It's conservation of energy, right? We have not derived any kind of equation for conservation of energy. And what I'm going to assert is that it's here, it's staring at us on the board, but we need to massage it a bit, okay? How are we going to do that? To do that, we're going to take this guy, the equation of motion, and we're going to multiply both sides by r dot, basically the velocity of our system. So if we take mu r double dot and multiply by r dot and set that equal to negative not the time derivative, the position derivative of our potential energy times r double dot, we're going to be able to pull out the energy. But you might be thinking, this doesn't look like energy. What's going on here? What's going on here? Well, let me write this a bit differently. First, I'm going to write this r dot as dr dt. And here, I'm going to write the following. And I'm going to prove it, okay? So this is no different than the time derivative of 1/2 r dot squared. All right? So let's work with the left side first. So where did this come from? It's like I pulled this out of thin air, right? This is something that crops up quite often. So once you see it, once you understand it, you may be able to do a trick like this, but the trick goes as follows. Let's evaluate this. Let's just evaluate this. So this is 1/2. We're going to take the derivative of r dot times 2 r dot. Now the chain rule, because r is a function of time, as is r dot. So we got to use the chain rule. So this is times r double dot. Well, look at that. This is no different than that, right? It's no different. So we just condense this down into one derivative, which simplifies it, but also divulges something interesting, right? Because what does this look like? 1/2 mv squared. We could pull that guy inside the parentheses, and it would divulge a lot of information for us. Now, I'm going to come back on the right side and put a t in here to emphasize that this is a function of time. Or rather, let's make it more explicit. It's a function of r, which is a function of time. All right? So, what this is saying is that this is no different than the time derivative of the effective potential energy, right? Right? Because if we take this, I'm going to write it down and explain it. I'll include r sub t. If we take this, first we need to take the derivative with respect to r, and then we use the chain rule because r is a function of time, right? So you do the first term, ddr, and then you take the chain rule of what's inside because it's a function of time. This is no different than that. So we just rewrote it. We rewrote it. So why did we do that? Why do we do that? Well, as you could predict, I'm going to take this over here, just sort of similar to what we did earlier in our analytical process with the equation of motion. We're using clever tricks. So I'm going to bring this inside, and I'm going to bring this over. And this just states that 1/2 r dot squared plus the effective potential energy does not change. Does not change. Okay? So that asserts that 1/2 mu r dot squared plus u effective is equal to a constant. It has to be equal to a constant in order for the derivative to vanish. So I'm going to say that that constant is E. Because when I look at this, what do I see? What is this telling me? What is it conveying? This is saying that the kinetic energy of our comet plus its effective potential energy is constant. That's the total energy E. That's the total energy of the system. Okay? That's what we found. Now, if we expand this out a bit, we can find that, look, we get 1/2 mu r dot squared. This guy is L squared over 2 mu r squared plus u sub r equals E. Well, what's this? We can plug in what this guy is and see what it can tell us. So we got L squared, which is nothing more than phi dot times mu r squared over 2 mu r squared plus u sub r. Okay? So in the end, we get the following. We get 1/2 mu squared divided by mu gives us mu. R to the 4th divided by r squared is going to give you r squared. So we're going to get r squared phi dot squared. I'm going to write that as that. So look at that. My E is messed up. Let me fix it. What we have here is just total kinetic energy. We have the translational kinetic energy, the angular kinetic energy, and the potential energy, right? This is the total kinetic energy because we have the radial motion. Omega cross r is just the angular motion. So when you take r dot squared plus the square root of the angular velocity, you get the total velocity. This is 1/2 mv squared. Okay, so by using tricks, we nudged out the kinetic energy, or rather the total energy in the system, and now we have this expression. Okay, so I'm going to write this up just to try to make some board space. So the total energy is 1/2, not surprising, r dot squared plus the effective potential energy. All right? So what we found is that the energy is going to be constant. It's a function of kinetic energy and potential energy. And now what we want to consider is how this affects this plot. Does it divulge any more information? Can it give us any extra idea regarding the behavior of this problem? You know, if we look at the energy of the comet, can we figure out if it's bounded? Can we figure out if it's unbounded? Is it going to fly off into space? What can I divulge? We're going to use this to become more acquainted with this problem, more acquainted with this potential energy well, and that's going to guide us through the analytical process of trying to solve this. Because, as I said previously, it's always important when you're analytically solving stuff, when you're chugging along in the math, you don't want to get lost in the semantics. You don't want to get lost in that mathematical language and be blinded to the physics. You want to ask what kind of concepts crop out. What is it saying to you? What is the language speaking? Okay? So next, we're going to consider what the energy divulged and see if that can give us any more information regarding the behavior of this problem. All right, so let's do just that. Let's take the energy equation we just derived, we just showed, and see if that can provide any information regarding what we were looking at with the plot previously. So the first thing we want to do is we want to make one important conclusion. If we take a look at this guy, the kinetic energy in the radial direction, the question I have for you is, what do we know about r dot squared? R dot squared is always greater than 0, right? Because if the velocity, the scalar value of it is negative, and you square that, it becomes positive. If it's positive, it remains positive. So this guy is always positive. What does that imply? It implies that our energy is always greater than the effective potential energy, no matter what. No matter what. Okay, so what does that mean? It means on this plot, motion can only exist in one region. In one region. This is the energy E. It has to be larger than our plot for U effectiveness. So I'm going to put in this hashed line here in green. Our energy is clean. It's green. It's renewable. So I'm just messing around. But anyway, our energy has to be greater than our effective potential energy, right? So we have to exist in this region. We are confined to the green hashed region. All right, we can't go below here because of this equation here. We are bound by this. The energy must conform to this. You see? So I guess that inspires another question. What happens when the energy is positive? What happens when it is negative? Right? It could still be positive, it could still be negative. This guy is negative. You add a little bit of kinetic energy on top of it, it can still be negative. Or this could be positive and you can add more on top of it. But we see that there are negative energies down here. And we want to ask what happens in both circumstances. Okay? So the option we want to consider first is the following. What happens if the energy is greater than 0? If we're above the 0 line, what kind of information does that convey about the motion? Well, I drew in this line here. It could be basically anywhere above this line. Well, what does this say? It says we could exist anywhere in here. Anywhere. Okay, so we could have, a minimum radius right here. And that happens when r dot is equal to 0. So when r dot is equal to 0, energy is equal to its minimum. Basically that. Okay, it's basically equal to the black plot. So this, the minimum radius. We look at this plot here, so you see the comet's going to come in, and it's going to have a minimum radius. Right there, right? That's what it is. But then we find something interesting. If the energy is sufficient, the next bound is infinity. And furthermore, we can take this guy here that we derived previously, say that This guy is a constant, or it's not a constant, but it's always positive. It's always positive. It's always increasing, right? So phi dot cannot switch signs. It cannot switch signs because if we have motion like this and constrained to a plane, which we found out previously, the angular momentum vector is coming out here. We know angular momentum is conserved, it's constant, it's a fixed L value, so it basically has to go in one direction, right? If it's negative, it may be the reverse direction, but what that means is that if we're tracking the angle between this horizontal and the comet, it's always increasing. It's always increasing. So if it's here, it's come in towards the sun, it has some minimum, it's going to stop abruptly, instantaneously, when r dot equals 0, and then it's going to fly out further. What does that mean? What does that mean? It means that if you have sufficient energy, the comet is going to be in an unbounded orbit. It's going to come in, sweep around, and slingshot out. That makes sense. It makes sense. In order to escape a potential energy well, you must have sufficient energy to do so. Sufficient kinetic energy to fly out, in essence. But now, what we want to question is, can it be bounded? You know, if the planets are going around the sun perpetually, maybe the comet would too. What does this framework convey without actually solving it? Well, if you take a look at the point in which the total energy E is less than 0 down here, we find something very interesting. Okay? We find that we're stuck to this green hashed area inside here, and we find that it crosses the effective potential energy at points when r dot equals 0 at two places, at a small r and a large r. And it looks like it's stuck between these two distances, right? It's stuck in this region. It's stuck. So this is another minimum, r min, but this says the energy is not sufficient. If you did not put enough energy into your system, the comet is going to be constrained. It's going to be limited. It can't go out beyond our region because the gravity is going to pull it out. It's going to pull it back. Right? It does not have sufficient energy to overcome that gravity. Right? It needs more energy to get out of that orbit. Okay? So let's explore this scenario a bit more. So in this situation, we could have the sun and the comet is going to basically come in, reach a minimum area or minimum radius, come out, reach a maximum, and come back. So if we draw in the comet, we draw in the same trajectories. This guy is the minimum radius. But this guy is the maximum radius. So what we see is that r min and r max can only occur when r dot equals 0, when it abruptly stops and when we're equal to the effective potential energy. So we also know that phi dot is always going to be constant. So this guy is always going to be going in one direction. And that means that the comet is going to come in, going to reach that minimum point where it stops abruptly, and then it's going to reverse sign. Then r dot is going to start to increase. It's going to start going in that direction. Then it's going to reach a maximum point where r dot equals 0, and then it's going to reverse sign and start going back and forth, back and forth. This is a bounded orbit. Okay, in essence, again, the energy is not sufficient to overcome the pull of gravity, and it is perpetually trapped within this well unless some external force, some external entity comes into play, right? Maybe it's going along, another comet hits it, a transfer momentum, it's going to affect its energy. Or maybe there's another planet that wants to pull it further. Again, changes its energy. Unless something comes into play to affect this, it is perpetually trapped in this potential well. And this is behavior that we not only see in this problem, in the Kepler problem of planets and comets orbiting the sun, but it's behavior we could use for any kind of central force two-body problem. So, as I mentioned previously, you're going to see this crop up again. Very important graph. This arises, and also this behavior we just examined arises whenever we have two bodies with a central force intact. It happens with the diatomic molecule, right? In quantum mechanics, you'll first study things known as potential wells, infinite potential wells, square potential wells. In essence, if you don't have enough energy to get up out of this well, you're potentially or perpetually trapped in that energy well. Okay? So, I thought it was important to take a step back, take another look at what we've done. You know, we've seen the analytical advantage in the sense that we only have to analyze one equation of motion as opposed to 6, because we reduce 6 degrees of freedom down to 1. But we did not really take a look at what we gained from a physics perspective. Okay? So what we found is that just by looking at this model, by looking at the equation of motion and the effective potential energy and our total energy, we were able to deduce a lot of behavior of this comet, of the Kepler problem, without having to rely on, solving differential equations, using complex math, a lot of exertion, right? We found that the comet is going to experience either oscillatory behavior or it's going to slingshot out. Okay, and that is all controlled by the energy that is inherent in the system. And it's not surprising because a lot of systems you analyze, it's just a play between the energy levels. Is the energy in kinetic energy or is it in potential energy? Is it going back and forth? Is there oscillatory behavior associated with that? Okay, so I hope you enjoyed that. I hope that gave you a clearer perspective on this problem. And what we're going to do next is we're going to go ahead and try to analytically solve this. We're going to have to use some tricks still, but it's going to be somewhat difficult. However, we know what we expect to find. So when we solve this and we get an equation of motion of where the planet or the comet is going to reside in the orbit at any given time, right? What you can do is you can drop back and say, okay, this is the behavior I expect. Did my math produce that? Is the math converging upon what I expect? Is it converging upon reality, right? We could compare it with astronomical data we get from astronomy, basically what Kepler did. Okay? So keep this in mind. Keep it in the back of your head. And as we run through this, don't let the math boggle you. Don't let it pull you down. You've got physical intuition. It's going to be your guide. And when you combine that with your intuit and your integrity, and you trust the math, it can lead you to nice, beautiful results. Stay tuned.